you guys are fair game. So thank you guys for coming.
All right. Thank you, everyone. So, yeah, I'm Matthew, and I'm going to talk about the ultimate pit problem and some other things like that. Should be pretty fun. I'll try to spare you guys a little bit of math, but I might do some. So we're going to click on here so that it's focused. Okay, open pit mine design. I don't want to talk too much about this. I'm going to assume that you have some amount of understanding. It is a circular engineering process, like most engineering processes, I guess, in terms of making decisions. Why is it circular? Because it's impossible to make a starting decision. Like, what's the first decision that you make when you're trying to design an open pit mine? I don't think there is one. You need to make a decision and kind of see how it plays out and then revisit that decision. One of the main problems that we're going to talk about is the ultimate pit problem, which is ostensibly a question of saying, do I mine this material or not that? Or how big is my mine going to be? Well, how can you answer that without knowing how long it's going to take you to mine, or what equipment you're going to use, or what your costs are going to be? And wait a second, your costs are going to depend on how long you're operating, which depends on how much you're mining, right? So all of these things are related to one another. So it's impossible to make just one decision to start. That's why I say it's a circular process. Lots of different concerns in open pit mine planning, things, financial concerns. Some of those are even out of your control. Some mines are in many ways dependent on the price of diesel, or the price of their commodity of interest, or any other kinds of prices that they don't really get to choose. Now, the finance people have ways of handling that sort of thing, but that's not what we're talking about. Other concerns, of course, geologic. Remember, we're mining actual material. We're mining the ground, and the ground, well, it is the way that it is, but we might not even know exactly how things are situated, and we might not know how much material or its properties. So lots of geologic concerns, geotechnical concerns as well, the strength of the material that we're mining, it just goes on and on and on. Environmental, of course. But the part that I like, the part that I'm interested in, the part that keeps me in this space is the optimization problems that are a part of it. If I could go back in time, I'd probably still stick with mining engineering, but I might go like industrial engineering or operations research, the math side, the decision. Oh, that's so much fun. That's my favorite. So that's part of what we're going to talk about, is some of those optimization subproblems in mining. And optimization is the process of making decisions. So we're going to be thinking about maximizing or minimizing some quantity subject to some constraints. Okay, and we'll get into that in a little bit more detail later on. To start with open pit mine modeling, we need a model. A model is, of course, something that we come up with. It's not reality. It's something that gives us an idea of the underground. We use it in our decision making. We need a model because we can't just, or else you're adrift. You have nothing to work with. So a model, a very common model in open pit mine planning is the block model. And a block model looks kind of like this. It's just a rectangular big grid of blocks. And we fill those blocks with various attributes. So geostatisticians will help us. The geologic engineers, geotechnical guys, everyone will help us in filling in our block model with a lot of information at each spot. One of the main things we might be interested in, what's the value of this block? But that's so hard. People have written tons of papers about this. Some mines that I worked at had like multiple page scripts to try and figure out the value of a block. How do you do that? You need to think about how much it costs to process it, to move it, if it has any contaminants. Oh my gosh, it's a big mess. But we're going to ignore that big mess, and we're going to imagine that you do have a value for each block. That's our block models. The next major thing that we need are precedence constraints. And a precedence, not in terms of something being more important than something else, but precedence in terms of something preceding something else, so happening before. So what it means is if we want to mine this block down here, we need to mine all of the blocks above it. We need to mine certain blocks above it, not every block above it, but we need to mine certain blocks above it that's dictated by those geotechnical friends of ours, right? So you could say, for example, that this block depends on the 5 blocks immediately above it and across. You're going to end up with a weird diamond-shaped pit, so don't do that. Instead, we might say that a block depends on all of these sorts of specially selected blocks above it, and then we end up with a nice, reasonable looking pit. We're not going to talk about that much either, but you do need to know for every block what needs to be mined before that block. This is the main difference to underground mining, right? Underground mining, you like leave stuff above you. It's a little scary. You need to be smart about it, but you can leave, you know, at least in open pit mining, you don't have to worry too much about something falling on your head, although it still might happen. Wear your hard hat, PVE, yeah. All right, let's keep going. Ultimate pit problem itself. The ultimate pit problem is to identify the maximum value, so the most money. We have that dollar value on each block. We want to maximize that dollar value. It's a subset. We're only going to mine some of them. That satisfies precedence constraints. If you just wanted to maximize the value, well, just take all the positive blocks. Kind of what an underground mine might do. No, they can't exactly do that. But, you know, take all the positive blocks. Instead, we have to pay for all of the negative blocks above us, all of the blocks that are going to cost us money above. Now, despite the name, we don't use this only for determining ultimate pit limits. In fact, if you determined your ultimate pit limits only with this method, well, that's kind of a bad idea. Because the ultimate pit problem has quite a few valid criticisms and valid problems with it. So some of the problems with the ultimate pit problem would be it doesn't account for anything like the time value of money. Of course, that's important. Time value of money saying often we want to maximize net present value. So we want to maximize our dollars today, accounting for the fact that a dollar today is worth more than a dollar 5 years from now. Right? So we want to maximize a discounted value or a discounted cash flow. If you're a mining operation, you want to pay back your investors, or you want to keep your bank off your back or whatever. You want money now instead of later. And the ultimate pit problem doesn't do that. Now there's tricks and things, but it doesn't do that. It is a very, very, very oversimplified, unrealistic model of mining. It's not imagining that we can extract a block by itself and get the money from it. Like, that's kind of silly, right? Mining, of course, even open pit mining has a lot of other considerations. You have to haul that material, you have to process it in a certain way, you have to do all these sorts of things, right? So it's a very oversimplified model of mining. And there's several other valid criticisms as well. However, despite those criticisms, it's still useful to have something. We need something to help us make decisions, or else we're completely lost. So the ultimate pit problem can help us make decisions. And we'll see some examples of that later, more than just on the ultimate pit. So, and also this is the part that I like, it has a very cute mathematical structure. So efficient. We will get into that just a tiny bit. So again, though, ultimate pit problem, we have values on a block basis. We have precedence constraints that says if I want to mine this block, I need to mine these. And then we determine a subset of blocks that you should mine. Now we're going to look at some tricks that you can play and some ways you can use this in different applications. So here is, for example, an ultimate pit that I've calculated. It's probably pretty hard to see in this three-dimensional form. So I cut a section through it, and this is the outermost boundary of that pit. So there's the A to A prime section. So it's those blocks that we have to mine. Of course, this was just like 45 degrees, but you can change that. So that's the largest one. This is the largest ultimate pit. That would be like, let's say we come up with some idea and we calculate our ultimate pit. There we go, we get that one. Well, we can start doing some things like, what if we just reduce the value of everything by a little bit, or reduce the value of gold and calculate the ultimate pit again? Well, then you're going to get a smaller pit. And you can keep doing that and get smaller and smaller and smaller and smaller pits, right? And that's kind of cool. What does that do? How does that help you? Well, if we do that in a reasonable way, it kind of gives you some indication of a reasonable sequence, right? So you could start with the smallest pit and then progress over here and then here and then here. It gives you an idea, it gives you a general sort of like idea of a schedule. Or a mining sequence. This is called many different things, nested pit analysis. You might have heard like the nested Lerchs and Grossmann thing, because those pits are all nested within one another, or parametric analysis, or there's different terms. And the parameter being something like your price, and you get this sequence of pits. This is just looking at it in another way. each of these bars correspond to a pit. So it has like the number of blocks, which is kind of like tonnage. Of course, you'd have to count for density and whatnot, but number of blocks is kind of like tonnage. And you can see as we reduce our value, we're going this way, or increase our value, we're going this way, you get different pits. And the number of blocks, the size of those pits changes. Now, one of the things that's kind of annoying with this process is that the size of the pits doesn't change linearly. It doesn't change in a nice line from here down to here. You can see we got these big jumps and bumps and these big changes in the size of the pit. And why would that happen? Well, it happens because you might have some valuable material down here, some negative valued material below it. You can think as the value is increasing, this is becoming worth more and more and more money, and then suddenly it pays for all the waste above it. And you get this big jump, right? So that can be kind of annoying, can be kind of a problem. These ones that I've highlighted are those that are nicely evenly spaced, right? And came up with a really cool dynamic programming algorithm to pick them. I know not many people are interested in that, but I think it's really cool. Like before, you had to do it by hand. You had to like go and say, I want this pit, this pit, this pit, but now it just does it for you. Anyway, I think it's cool. Maybe I'm actually planning to present that little thing at AppCon. So if anyone's going to be there, care about that, that'd be cool. Another application, another idea is that if you have a nice single estimate of your subsurface, your geostatisticians give you some nice smooth estimate, you would get one plan and one number. Well, sometimes geostatisticians like using simulation, giving you lots of different possible realizations. This is just a cartoon kind of explaining a little bit. So you could calculate the pit for all of them and you get multiple responses. So that's kind of cool. That's something that you can do. What's the main fundamental problem with that? Well, you're only really going to mine it once. I don't need 300 different plans. I want one plan that's the best in all circumstances. But that's, I don't know. Again, that we don't have anything to really give that to you at the moment. So, we can give you tools and things you can use as an engineer, make your decisions with these different possibilities. So one of the things you can do with this is you could create a map. This is plan view, and it's showing the probability at any block on the surface is inside an ultimate pit. And this is done over many different possible prices of gold, many different possible realizations of the subsurface, many different possible ideas, a whole big Monte Carlo style simulation, and we get the probability that a particular block is within the ultimate pit. Maybe that's useful to you if you were deciding where to put a plant or where to put a dump or something. You'd want to know, okay, I'm covering up blocks that are in the pit 50% of the time. That might be valuable to you. Now, these are long-range decisions. You're going to revisit them later. They're not set in stone, but this is all a big part of it, okay? I got a slide for all of you. Didn't think I'd let you off the hook that easily. We do have a little math. I want to show you just a little bit about the structure of the problem, which I find so cool. Okay, you guys remember this? Maximize. We want to make this number as big as possible. Sigma, that's a sum. We're just adding things together. It's just a bunch of plus signs. The VB, that's the value of our block. That's something that we kind of have an idea of. Multiplied by XB, which is our variable. Now that's only 0 or 1, so don't worry. Multiply a number by 0, it's 0. Multiply by 1, it's the number. So that's all it is, just maximizing the value of all of the blocks. And this is all your precedence constraints are. So for a particular block, depending on a block above it, it's just XB minus XB hat has to be less than or equal to 0. And all that does, you can think about it, there's 4 possibilities. If it's 0 and 0, is that less than 0? Yes, 0 minus 0 is less than or equal to 0. So we can not mine everything. If I had 1 and 1, 1 minus 1 less than or equal to 0, yes, we can mine both blocks. And of course the other one, and then the only problem occurs when you say 1 minus 0 less than or equal to 0, no. So that's it. That's the only thing that we're ruling out. We're ruling out the possibility of saying mine this block and don't mine the block above it. Pretty cool, huh? I think that's pretty neat. That's so tiny, you know, it's like, that's kind of cute. That's a big advantage because we can solve this very easily in a lot of different ways. One of the best ways of solving it is with the pseudo-flow algorithm. So this construction comes from Dr. Johnson, 1968. So the original Lerchs and Grossmann was 1965. This comes a little later. The idea is we take our ultimate pit problem here. This is a tiny ultimate pit problem. What is it, 6 blocks? Come on. So the 7 depends on these blocks and the 3 depends on these blocks. And we turn it, we rotate it 90 degrees on this slide, just because certain people are more interested in thinking of flow as going from left to right. And we are going to route some flow through this network. Now, I won't go into all the details, but if you do that, you solve for a very well-known thing, something called the minimum cut of this graph, then it is your ultimate pit. And that's great because a whole bunch of other people in operations research in other fields and other places, they like the minimum cut problem too. They like max flow and minimum cut for doing things like image segmentation. You can use it in different traffic networks. If you imagine cars instead of, well, we're imagining dollars flowing around, but if you imagine actual vehicles and stuff, you might be interested in given a road network, what's my bottleneck or where can these cars go through? Lots of people care about this problem. In fact, it's probably used on your phone in Google Maps when you say to go somewhere else, you know, at least in some part of that process, they will be calculating this style of result. So that's great because in the mining industry, we don't have to come up with the best way of solving this problem because they already have in other contexts and other places, right? So we can use that. We can use this clever reformulation of the problem to solve. So I'll go through a little bit more details because I didn't spend so much time on the pseudo-flow algorithm for me not to waste at least a little bit of your time in understanding it, okay? So you're just gonna have to forgive me for this. It was inspired by Lerchs and Grossmann, came from 1965. That was the original thing. These two Canadians, mining engineers came up with this approach to solving the problem. Hotchbaum was actually commissioned, so she's a researcher. I forget the school, I shouldn't have started that sentence. And she's a researcher who then was commissioned to work on that problem, but she kind of noticed something a little bit about how Lerchs and Grossmann were solving this problem that then she could change, she could apply in a different sort of way that ended up eventually becoming the pseudo-flow algorithm, which is the current best sort of practice for solving the ultimate pit problem. So it involves setting our form up in a similar way. This time again, sorry, I rotated us back 90 degrees and flow is now going up. And we have these different concepts here that of flow, of dollars in this case, flowing along arcs and things like excesses and deficits. I'll go through an example very quickly. The way that it starts is it imagines as if it was like an underground mine and it could mine just every positive valued block. So every positive valued block becomes initialized as something strong. We're going to mine that. But we have these negative valued blocks above and they're ruining our day. So we need to pay for them. We need to pay for the negative blocks above. So that's the initialization again. What we're going to do is we're going to take, for example, the money that's in this block. Remember it had a value of like 3. We're going to take that money and we're going to send it up to pay for the block above it. So we send those $3 up. And then because that block only costs 2, we have $1 left over. Perfect, right? So we have $1 left over to play with over here. So let's try and pay for that block now. Oh, that's a problem. I only have $3. I sent 2 to him and 1 to him, and I'm left with negative $3. Oh no. So I don't mind that. This is really how the algorithm works, right? It really operates in this fashion by introducing these arcs. It's just you can get clever in the programming side to make it better. So then we pay for this one and this one and this one. Now here we have a little bit of a snafu, something we need to watch out for. We need to be very clear that if this block down here, remember he had $7 to play with. After he's paid for his blocks, we need to be very clear that this block is not helping him in some unfortunate way. We want to be very careful to not allow stragglers, these different blocks that aren't actually paying for the blocks above us. They can't help him. They have to pay for their own thing. So that's the main character of the algorithm. There's a lot more going on, but that's the main character of the algorithm. Now there's things that we can do Remember, Hotchbaum, inspired by the mining industry, but developed it for everyone else, right? She developed the Hotchbaum algorithm to help everyone else, right? And like in these different contexts. But the mining problem, our problem, is a little special. It's a little bit different. And we can do some clever tricks, like these precedence constraints. We don't need all of them to begin. I can generate them as I need them. This is a huge increase in decrease in computing time, increase in how fast it is, okay? This can save us a ton of time if we generate those precedence constraints lazily. The other thing, and this is, I think, kind of neat, the way that our problem is structured, positive blocks only ever send money to negative blocks, in a sense, right? You only have positive on one side, negative on the other. It's this bipartite structure. That's not the case in things like roads. If you were imagining roads, cars might be going this way, and they might be going the other way. But in our particular case, dollars are only ever going in one way. And we can take advantage of that to improve our implementation of Hotchbaum's pseudo-flow algorithm so that we're faster, yet again. The other thing is, Hotchbaum developed her algorithm to calculate the maximum flow, which is a different kind of concept to the minimum cut. I won't go into all the details, but we only care about the minimum cut. We don't care about the maximum flow, so throw all of that out. Seems like reasonable sort of course of action, reasonable thing to do. If you do that, you get our optimizer, so that Dr. Daglin, Heiss Johnson, and myself, Dr. Johnson and myself worked on, called it MindFlow, cool name, flow. I don't know. It's an ultimate pit optimizer, flexible, block models, precedence constraints. Correct. I did check it. I made sure it's correct. But it's very fast and memory efficient. So that's kind of neat. The other thing with it, oh yeah, fast and memory efficient. Ah man, big table of numbers. That's a mess. These are different data sets, different problem instances. This one, for example, has 16 million blocks. 16 million blocks, that's a reasonable sized model. I've seen them get bigger. I've seen them a lot smaller. They don't get bigger too often, but they do sometimes. And these are the solution times in seconds, the average middle of 5 runs from different commercial packages. I won't name names. MapTech is on this list. Deswik is on this list. A few other commercial packages are on this list. In terms of time, these guys take 12 minutes to solve this model. 12 and a half, kind of 3 minutes and so on. But MindFlow, oh yes, you always put your results farthest on the right, 9 seconds. Pretty cool, huh? That's pretty neat. That's taking advantage of that structure. That's generating those precedence constraints lazily. And why is this important? Well, what was the applications that I were talking about? Often the applications of the ultimate pit problem, you're going to solve hundreds or thousands of different possibilities. And you start multiplying this number by hundreds and thousands, and your hair is not going to happen. You're going to get tired, you're going to turn the computer off, and you're going to make suboptimal decisions. Whereas if we can compute the results very quickly, then you're happy. So always faster. Yay! And, oh yeah, I put it on a chart. I think this chart kind of doesn't look very good because MindFlow here in dark blue, that's the one the farthest to the right. It's so small, you can't even see it. You get a little blip of it right there, but you don't even sit there, and that's the time. Seconds. What are these guys doing? No, a lot of it does come down to, a lot of them will generate all the precedence constraints right away. It's silly. You don't need them, so don't do it. Anyway, C++, blah, 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 blah. Open source, totally free to use, completely free to use. GitHub.com, MindFlow CSM, MindFlow. That's pretty cool. It is, we wanted to help, help researchers, help put our research out for other people to use in this sort of, if you're doing this operation, and extend it. And if other people want to use it and come up with other ideas or come up with other improvements, then they can do that. We can kind of work together. A lot of these other packages, you're paying $20,000 for a license, $2,000 a year in maintenance. Maybe more than that, because you probably need the base package too. You're probably paying $70,000 for a license, if not more. So, it doesn't have a fancy interface, but who needs that when you're doing it thousands and thousands of times, right? You can set it up. Okay. How am I doing on time? I'm doing okay. I'm not going to take the whole time. Don't worry. We're going to do now, let's start talking about minimum mining with constraints. So why did we go through all that work? Well, we wanted to extend the problem. We wanted to push the problem forward. We wanted to handle something else. We wanted to do something that hasn't been done before in a really solid way, in our opinion. So we wanted to start handling minimum mining with constraints. And what does that mean? Well, if this is another cross-section and you're mining down, you can't mine an individual block. You need to put a shovel there. You need space to operate in. We're not mining with teaspoons and helicopters. We're mining with large pieces of machinery. They need space to operate in. So we'd like to put that space to operating in, that minimum mining width, as a constraint into our optimization. Seems like a good idea. It's kind of tricky though. We'll see that in just a second because it messes everything up. Ah, man, we had such this beautiful structure and now we're just going to destroy it. Anyway, it's so cool though. We'll get to that in a second. The thing is, doing this by optimization is very important because the way that it's typically done is your mining engineer just calculates the ultimate pit and then kind of chops off some blocks at the bottom or draws it in a different way. And they don't account for the value that they could be leaving on the table. This example, I won't go through all the details, but it's important for us to expand to the left instead of expand to the right because we get a little extra money. It's important, right? Doing it via optimization is the best way to make this decision to handle these minimum mining with constraints. So here, just 3 examples, just 2D examples. So here's our block model. That's with a minimum mining width of 1, the original problem. Don't need to do anything if that's the case. Minimum mining width of 2, we get a slightly different result. Excuse me. Minimum mining width of 3, we get another different result. Cool. In 2D, I can solve this problem again with a cool dynamic programming algorithm. Won't go into the details yet again, but it's very cute. You can read my thesis, and you will agree that it is very cute. But it only works in 2D. Oh, that's a problem. In 3D, we need to do other things. That's another 2D example. Oh, looks like I put some more math for you guys. Make sure you're all awake. Here's what it looks like. Here's what the problem looks like. Yet again, we want to maximize our value. We have mining with constraint, or excuse me, precedence constraints, exactly the way they were before. But now we add these little M's, and each M corresponds to a group of blocks. So each M corresponds to the group of blocks, and you'll see that this constraint is exactly like this constraint. And what it's saying is that if I want to mine, if I want to say that that entire group of blocks is mined, every block inside it has to be mined, right? If I wanted to say that a group of blocks is extracted, every block inside has to be mined. It's really that simple. That's what this is saying. But then this is the tricky part. This part says, if I want to mine a block, I have to mine at least one of the groups that it's a part of. It's so ugly. It's saying like, okay, it's going backwards, right? We're saying, oh, I want to mine these blocks. This is perfect. I want to maximize value. I want to mine these blocks. It makes a ton of sense. But then it's stopping us. It's stopping us in our tracks. It's saying, no. If you want to mine any block, you have to mine at least one of the mining widths that it's a part of. Oh, this is so gross. It ruins it. So let's cover it up. I'm not kidding. This is a great way to solve problems in your real life. If you have problems in your own life, just put them under your bed. You have dishes, don't want to wash them, just shove them under the bed, and at least that problem, hey, problem's gone, nothing to see here. Don't need to worry about it. We'll just cover that one up and solve the problem and go along with our day. Oh, wait a second. Sometimes that doesn't work. We actually need to do something a little tricky. Instead of just covering up the problem, although we do that, we do. When we solve it, we first solve it without any mining widths, because what if the answer satisfied our mining widths? Then we're done. That'd be great. Never happens, but it would be great. So we do that first. We do cover up that constraint. Just forget about it. The next step though, can't really just cover it up. So let's put it somewhere else. Let's put it in the objective. Anyone know what this is called? When you take a constraint somewhere you don't like it and you put it somewhere else? This is it's called Lagrangian relaxation. A really relaxing thing to do. Really helps with our problem. Look at this. This problem is beautiful. It's exactly the way that it was before. We have some objective, ignore this. We have some objective, and then we have our ultimate pit problem down here. Everything is perfect, but these lambdas, it becomes a bit of a problem. But that's fine. I won't dwell on the details, but if we could find the right lambdas, the correct lambdas, the ones that are best, and there's techniques for doing this, we'll get our answer, and it'll satisfy minimum mining with constraints, and then this was a reasonable thing to do. Hopefully that math was at least somewhat accessible. Here's a 3D example. This is using what we were just talking about. So these are planar cross sections. The red is the ultimate pit, and we say that doesn't satisfy our mining width. This is a relatively low down section. We say it doesn't satisfy our mining width. That's why it's red, because we don't know. For these blocks out here, we can't fit a shovel in there. We can't fit a shovel over here. We can't do that. So we kind of have to make some choices. We remove certain areas of the pit. We expand in other areas. So here it's actually expanding and removing, and it's doing that by optimization. And because we have a really fast solver, we can solve a lot of times, and that's what helps us. So we can, before this problem took like, several minutes for these commercial solvers to solve. We're doing it in 0.14 seconds. We can even put our mining widths in there for 2.3 seconds. And look, we only cost you $500,000. Of course, the value is going to go down. How could the value go up? I'm making the problem harder. The value is going to go down. It's not going to be as good of a pit anymore, but at least you're going to be able to mine it, right? And if you were to do this by hand, it would go down even more. So our goal is to make the value go down as little as possible. So that's cool. Mindful of MW, mining width, makes a ton of sense, huh? Oh, here's a 3D example. Open the pit. And with a 5x5 mining width, doesn't look that different, huh? That's the point. It's not supposed to look that much different. It's supposed to just satisfy your mining width now and be a reasonable shape and only lose the barest minimum amount of value. So you can see it. If you look over here, you can see some tiny little spots. And if you look over here, you can see these larger areas that you can work with. And now we can use our ultimate pit optimizer that handles mining width in all of those fancy applications that I was just talking about. Why can't we just use it directly in all of those circumstances before and make even better decisions? Aha, I think that's a good idea. I hope you do too. Because I spent a lot of time working on it. Oh, good gravy. Hope I didn't waste it. Lots of little things that we can do to make this faster, to make it better, to add detail, to make lots of things. Tons of heuristics and methods. Here's a good point for you guys. Anyone out there thinking about doing any kind of optimization? Don't put all your chickens in one basket. No, eggs in one. Don't do that. Don't put all your eggs in one basket and imagine that only one optimization technique is the best technique for you. Try a whole bunch, because in some cases, some might be better than others. So we have tons of different heuristics and approaches to try and do this alongside the Lagrangian relaxation, which is the most theoretically justified approach. We have other heuristics too, to give us some sort of ensemble optimization. Computers these days, they don't care. You could ask a computer to compute the millionth digit of pi, it's not going to complain to you. You ask your kids to do that, they complain. What's up with that? But I ask my computer to do it, it's fine, right? They don't care. Just give them a whole bunch of stuff to work on and get an answer eventually that'll help us make better decisions. That's where something like ensemble optimization will help you. The dynamic programming algorithm, I would love to come back. If you guys invite me back, we'll talk about dynamic programming for an hour together. We'll have a really fun time, right? I have a really good time doing dynamic programming together. It's cute. Oh, the other thing is, and this is such a pain. This is such a bear, but I got it. Actually, Dr. Daglin doesn't know that I got it. I got it just like a week ago. And I proved that my problem is very hard. Why did I do that? Why did I prove that the ultimate pit problem with minimum mining width is something called NP complete, which just means hard problem? Because it gives me an out. It saves me. Because I've proven mathematically that no smart young person is going to come around and show a polynomial time algorithm for my problem. They're not going to come up with a polynomial time algorithm for this, because if they did, they would be the most famous person in the world. You know, the P versus NP complete problem, probably heard of P versus NP, one of those millennium problems. You get $1 million if you solve it. You get a lot more than just $1 million, but there is actually $1 million set aside for if you solve that problem. And that would be the only person that could show that my particular problem is easy. That might not be exciting to you guys, but it was really exciting to me. It's really important to show, to prove mathematically that only someone who would get $1 million for doing it would show that my particular problem is easy. Remember, the ultimate pit problem by itself, that's easy. We can solve that in polynomial time. But this, mining with constraints, nope, not easy. So that's good. Saved myself a lot of stress by doing that. Oh, look at this. Some other things that it can be applied to. I just like this picture, okay? I made this picture a couple years ago. It's for a different project that I did before this. That was a grade control optimization problem. Grade control, short-term decision making. We want to look at mining, you know, we want to mine reasonable polygons. This would be, you know, I would send these blocks to the mill, these blocks to the leach, this block to the dump. This is a blast. For example, this is a real one from a real mine. Lucky them, look at all that blocks going to the mill, all those green blocks, jeez. Anyway, we want to make this more mineable. We want to say, you can't just send an individual block in the middle of a bunch of blocks going to the mill of the leach. It's not going to happen, right? These are big machines. They're not going to do that. So we need to clean it up. We need to make it better. We need to reclassify those blocks. But we want to lose the least amount of money doing that. So this is grade control optimization. This is it's a module in Vulkan. You can buy it. People use it, actually, surprisingly, around the world to make decisions. They also use it for weird things. They don't use it just for grade control. You can use it in a long-range planning context. Everyone in Europe and Africa does it that way. I don't judge how you use these tools, these optimization problems. Another one is this whole sequence. So just making them satisfy mining lists, these are again vertical sections now, just making them satisfy, you know, something like this. That's not really the best thing to do. Really, if we were going to put a ramp in here, we don't want to move this wall again. So we need to, you know, there's other constraints that come into play. But if even just these tiny simple constraints ruin the structure of the problem, what the heck are these going to do? Oh, man. Well, future problem potentially. And hey, that's that. So thank you very much. I'm done. Questions, concerns? And look, I didn't go over time. I always have a timer. I had an experience once where like I get talking right pretty quickly, and I had like half an hour to present, and I was done in 15 minutes. That was a little embarrassing. There was a lot of like, any questions? Any questions? And then I had it the other way too, where I just kept talking. Huh. You guys are lucky you didn't experience that. Any questions? My plan when I'm done with this? Well, I am currently still working at MapTech, and I will continue to work at MapTech at least for a while. And then maybe eventually I have some secret plans involving writing my own stuff. But we'll have to see how that goes. You know, they've taken so much advantage. Oh, we're recording. No, I'm just kidding. I love it. It's been fantastic. Okay.
All right.
So the reason that I went for the minimum mining width route, because I thought it looked juicy. It looked like I could get it. It looked small enough that I could get it. One of the things that like a lot of people in their research, they try and change the world. You try and make a brand new model of everything. And like, that's hard, right? It's hard because, well, there's a reason that people haven't done that yet, most likely. And, you know, also it's hard to sell people on it. this is just a little option in something you already use. Why wouldn't you use it? Very more broadly applicable. So I wanted my research to be around something that people have literally asked me before to do, and also something that I think would be valuable. All right, let's go.
Good job, Matthew.
Thank you. Where did mid go?
All right, so anyone wants to secret? Sure. We're going to stop.
Amid, should I end this? Should I end the meeting?